It's happening and today, thanks to the visitor program that I have to acknowledge, the Oxygen Foundation through the Severo Ochoa visitor scheme. So just to properly introduce Rob. Rob is it's happening and today, thanks to the visitor program that I have to acknowledge, the Oxygen Foundation through the Severo Ochoa visitor scheme. So just to properly introduce Rob. Rob is it's happening and today, thanks to the visitor program that I have to acknowledge, the Oxygen Foundation through the Severo Ochoa visitor scheme. So just to properly introduce Rob. Rob is it's happening and to Do you want me to repeat the introduction? So I was about to say that Rob is one of the leading scientists in the study of accretion and jets and on stellar mass black holes over his career. I mean, he has many influential papers, but I think more important than that, if you look the landscape of the field in any conference, you will recognize that in the different aspects of accretion into black hole, the leading people is often people that were former Rob students or former postdocs. I think that is a great achievement and contribution even beyond his implementation papers. Rob, I think you were faculty in Amsterdam, Southampton, and now is full professor in Oxford, where he is leading a group. He is holding an Synergy ERC grant, and in the past, he held also an advanced ERC grant and was honored with the Herschel Medal of the Royal Astronomical Society. On a personal basis, I think that I knew about the system of Rob something like 20 years ago during my PhD course. He had Rafael Bachiller giving the radio astronomy course, who is one of the most famous Spanish radio astronomers. And he told us that for the course, we should read a review on a paper that was relevant for your field. So he was lucky or wise enough to pick your 26th review, I think, Rob, that actually, I checked this morning, was published in 23, uploaded to arXiv in 23. I loved that review. And so I thought, okay, I wanted to work on this at some point, and at some point join your group. I was lucky enough to do it in Southampton, then in Oxford. So me and the group were pleased to have it here. So the stage is yours.
Thank you very much, Teo, for the very flattering introduction. I'm delighted to be here. Between 2019 and 2024, I had a largely administrative role at the University of Oxford, and I've just rotated off that role, and it's an absolute pleasure and delight for me to be able to come here now for this month and get 100% back into research. So my main employer is the University of Oxford. I'm also lucky enough to be a visiting professor at the University of Cape Town, and that's relevant because I'm going to show you a lot of results today from MeerKAT, which is a fantastic radio telescope based in South Africa. A lot of the research I'm doing right now, and some of the research I'm going to present in this talk is funded by my ERC Synergy grant. So I'd like to thank the Occident Foundation for supporting my visit here to the IAC. Okay, so my talk's going to be a talk in 4 parts. 3 of those parts are relatively short. Part 3 will be the longest part, but occasionally you'll see these screens pop up during the talk so that you have some sense of the progress through the talk. So I'd just like to give a little introduction on black holes and on X-ray binaries. So black holes in general, I find myself very lucky and still very excited and stimulated to be working on black holes. I'm interested in other aspects of astrophysics, but they truly are, some of the most important and extraordinary and unusual objects in astrophysics. The particular type of black holes I work on in general are black holes in systems called X-ray binaries, and these are stellar mass black holes. These are black holes typically around 10 solar masses. And the particular aspect which I largely, but again, not exclusively focus on is the jets from these sources. So here's a schematic of an X-ray binary, and here's an artist's impression of an X-ray binary. So an X-ray binary system is one where you have a companion star, which is essentially an orbiting fuel tank for the accretion processes which go on very close to the black hole, or neutron star. So this class of objects, X-ray binaries, are also known as microquasars. The two are essentially synonymous. Sometimes people ask me, what is the difference between the two classes? There isn't really a difference. Microquasars was coined, not only is it, of course, a very good word for drawing attention to the field, but it was also coined because there was a time when people thought that maybe only a subset of X-ray binaries produced jets. We are now pretty confident, in fact, very confident, that all X-ray binaries at certain phases in their accretion cycles produce relativistic jets. And so these two terms are essentially synonymous. There's a point which is important and relevant, so I'll mention it now and I'll return to it later, which is these objects are discovered in X-rays. I mean, this is fairly obvious from the name, but what this means is that they are discovered as an isotropic sample. The X-rays we see from these objects are essentially isotropic. They're not beamed, and this means that we largely see a population of objects where the jets are very off-axis. And in fact, compared to most other sources of relativistic jets in the universe, this is highly unusual. So you have, stop treading on that tile. So you have a companion star, which is essentially an orbiting fuel tank. You have an accretion disk. Matter feeds through the inner Lagrangian point. It slowly loses angular momentum, descends in the gravitational well of the relativistic object. Relativistic jets are formed. One of them will be slightly more approaching and one will be slightly more receding. Hence, one will be slightly more blue shifted and one more red shifted. In fact, again, as something I'll return to later in the talk, often for X-ray binaries, both sides are red shifted, which is something you don't see in most other classes of objects. The jet produces primarily, or the radio emission, or rather I should say the wavelength regime in which we're most easily able to identify emission from the jet is the radio band. The inner accretion flow emits very strongly in X-rays. Now, those of you, if there are any people in the audience who work on AGN, you also have a black hole with an inner accretion disk and a jet. The jet still produces radio, but in that case, you'll be seeing emission largely from optical and UV regimes because the temperature of the inner accretion flow is lower. So let's talk a little bit about X-ray binaries and their place in the universe. So we are fairly confident that we understand how stellar mass black holes are formed. They are formed when a massive star undergoes collapse at the end of its life. They are also probably formed sometimes when neutron stars merge. The neutron star merger event, GW 170817, produced a remnant with a likely mass range of about 3 to 4 solar masses. Although we haven't directly measured anything from that remnant, it's almost certainly has produced a low mass black hole. So we produce a black hole. Some of these black holes will migrate towards the centers of their galaxy through a process known as dynamical friction, essentially through dynamical or gravitational interactions with other massive objects in the galaxy. They'll slowly migrate. They will grow via accretion and also via mergers of black holes. There will be interspersed phases of very strong accretion, high luminosity, powerful jet production. So this would include phases of accretion and growth via tidal disruption events. And then ultimately, these will produce the most massive AGN. The black hole X-ray binaries are black holes where the black hole remains at about 10 solar masses and finds itself in one of these binary systems. And then the vast majority of black holes which are formed via stellar collapse, at least for galaxies of the age of ours, which is essentially the Hubble time, actually end up as isolated black holes drifting through the interstellar medium, accreting at relatively low rates and not interacting a great deal. So black holes permeate the universe in space and time on all scales. The lowest mass black hole we know of is probably the LIGO merger event at 3 to 4 solar masses, and the most massive black holes we know of in the most massive AGN are around 10 to the 10 solar masses. And of course, James Webb observations are showing that there are massive black holes very early in the universe. So they really permeate all time scales and all mass and distance scales in the universe. They are one of the most important components for the growth of structures in the universe. I'm sure you're all aware that there are strong arguments that massive black holes regulate the growth of galaxies, and they are associated with nearly all high energy astrophysics processes. Just out of interest, if we look at the estimated numbers of these different types of black hole within, for example, our own galaxy, we think there is probably one supermassive black hole, that's Sagittarius A star. It's a relatively low mass supermassive black hole with a mass of 3 to 4 million solar masses. There are of order 5 or 1 to 10,000, I should say, X-ray binaries estimated within our galaxy, maybe a few more. And there are estimated to be 100 million isolated black holes within our galaxy. So in fact, the total black hole mass within our galaxy is actually dominated by the isolated black holes which are drifting through the interstellar medium. These objects, all different classes of black holes, also produce relativistic jets. So you'll be aware, and I'll show some images later in this talk, of these long, narrow, collimated flows which carry a lot of power away from these black holes at very highly relativistic velocities. Pretty much all of these relativistic jets from black holes are kinetically dominated. This, again, is an important point when we're trying to work out the total power of these jets. We can sometimes get a snapshot and measure the internal energy of the jet, but it's actually dominated by its kinetic energy of motion, at least when initially launched. And again, I will return to this, but observing deceleration of these jets is a key way to understand how they deposit this launch kinetic energy in the surrounding medium. So we have AGN feedback in clusters. The most massive galaxies Ideally, this would actually be an elliptical galaxies, sit at the center of clusters. The AGN produces very strong feedback. Tidal disruption events, which are lower mass black holes, maybe 1 million to 10 million solar masses, occasionally disrupt a star, and we know at least in a few cases produce relativistic jets. And on a stellar mass scale, we have GRB jets, which are probably the most relativistic flows in the universe, which correspond to the birth of a stellar mass black hole. And then we have those from the X-ray binaries, which I'll be talking about today. And one of the things they do is heat the ISM within our own galaxy. If we look at AGN jets, then probably the maximum Lorentz factor for these is something like 30 or higher. But the trouble with AGN jets is that they're essentially frozen in time. So I'm going to tell you today, later on in the talk, about 1 to 3 years, typically, of observations of jets from a stellar mass black hole. If you scale that up to the typical mass of an AGN, maybe 10 to the 8 solar masses, this would require the very first humans who evolved 2 to 6 million years ago in Africa to have started radio observations then in order to have covered the same equivalent mass scale, time scale that we have seen in X-ray binaries. Jets from TDEs, there's good evidence that some of those have Lorentz factors of at least 20. These are very hard to image. There is essentially 0 or 1, depending on what you believe, clear, direct confirmation of images. GRB jets are even harder to image. There are some tentative VLBI observations of expanding components from GRB jets, but that's essentially very hard to do. X-ray binary jets seem to have perhaps lower Lorentz factors, and historically, though, they faded away too quickly for us to do good kinematics and understand what was going on. But this is no longer the case, as I will show you shortly. And then there is a big exciting thing happening right now in this field, and I was lucky enough to go along to a talk 2 weeks ago that Alithia gave here. It turns out that the X-ray binaries within our galaxy are very high or even ultra high energy particle accelerators. So there are observations and detections of all of these classes of objects by Hess, MAGIC, HAWK, and now LASSO. And it seems that the interaction regions where the jets are interacting with the interstellar medium are the regions where very high energy particles are being accelerated. This is from a paper that came out from the LASSO collaboration just a few weeks ago, where they've reported detections of 5 different X-ray binaries at very high energies. And in the case of SS433, these very high energy emission regions are actually spatially resolved. So just to give you an idea, this is about 1 degree across. There is an X-ray binary, famous source called SS433, which sits here. This faint blue thing here, which is approximately circular, is probably the birth supernova remnant of this source. And there are distorted regions, which are the long-term action of jets from this system hitting the edges of the supernova remnant. And these, the red parts that you see here, these are the very high energy emission, which are happening when the jets are interacting with the surrounding medium. Completely immodestly, I will say that the first paper to suggest that actually the combined impact of jets from X-ray binaries could affect the cosmic ray budget of the galaxy was a paper that myself, Tom Macarone, and a student, Zdenko van Kesteren, wrote about 20 years ago now. And of course, this was just accumulating or totaling up all the probable energy input. There are more important and more detailed papers since. Okay, so that was the first part of the talk, which is just the introduction to the field. I want to say, I'm going to show you a lot of results from the MeerKAT radio telescope, and I want to say a little bit about MeerKAT. So I've worked on a few radio telescope projects over my career. MeerKAT has been by far the best. It's been by far the most rewarding to work with. The data are superb, and working with the entire organization has been absolutely incredible. So this is a real image of the core of MeerKAT. MeerKAT has 64 13.5-meter dishes. MeerKAT was inaugurated in 2018, which is around the time that our large survey program on the project began. I was lucky enough to be in a plane that flew out to the inauguration, and when we passed over the last of the hills that shields the telescope at ground level, we could see this gleaming array of 64 new dishes in the Karoo Desert in the Northern Cape of South Africa, and it's absolutely stunning. The project was originally conceived as part of the SKA Africa bid, and MeerKAT will become sometime in the next 3 to 5 years, the mid-frequency component of the Square Kilometre Array project. Okay, so let me show you some images from MeerKAT. This is the most recent version of one of the most iconic and famous images from MeerKAT. This is the center of our galaxy. Sagittarius A star lies in here. This is many degrees across. It's a composite image. This was produced by my friend and collaborator, Ian Hayward in Oxford. This is a real image. This is not in any sense an artist's impression. This is completely real. There is a lot of structure here. A lot of this is ionized gas. A lot of it is accumulated emission from many supernova remnants. Some of the supernova remnants you see more clearly, for example, this one down here. You'll also see very strikingly in this image, all of these long, thin filaments, sometimes which bend or have kinks in them. I should say that the origin of these filaments is really still largely unknown. There are papers offering interpretations, but it's really not entirely clear what these are. Allow me to zoom in. I should say this is not a complete non sequitur. It is not that it is not associated with my talk at all. There is a tiny little structure there, which you won't see from the back of the room, which is actually a black hole X-ray binary producing a small jet. This tiny little jet here is about 1 arc-minute across, which gives you a sense of the scale of this image. So this is a zoom in of the region. This is a supernova remnant. This is a neutron star, which was produced in this supernova remnant to the best of our understanding, and it's basically flying away through space at several hundred kilometers per second, leaving a trail behind it. And again, you can see some extraordinary structures. This source here is this black hole system that I was referring to just now. And this source is a source known as the Great Annihilator because it was postulated for a long time that it was a source of 511 keV emission from the galactic center. And it was also, in fact, the original microquasar. This was the source for which Felix Mirabel first coined the term microquasar. And I'll just zoom in one further time to these images. So this now, you can see there is a black hole in there. There are arc-minute scale jets coming from this, and these are dwarfed by these extraordinary structures that we see in the galactic center. So I began in 2018, co-led by my collaborator, Patrick Wout at the University of Cape Town, a monitoring program of stellar mass black holes and neutron stars within our own galaxy. So what I'm going to show you now is a movie projected in galactic coordinates. So this is galactic longitude, galactic latitude. And every time you see a source where there is strong and variable radio emission from an X-ray binary in our galaxy. When you see a red source, then it means we actually resolved large-scale jets, which I'll come on to shortly. Cyan sources are black holes, and there are a few bright neutron stars as well. So every time you see one of these flares occurring, this means that there is a phase of typically a few months where the accretion rate was very high. These produce powerful jets which propagate into the surrounding interstellar medium, which we're able to track typically for a few years with MeerKAT. So this is essentially a real-time census of relativistic jet production and particle acceleration within our galaxy. MeerKAT's at a latitude of just north of -30 degrees, so it's able to see nearly the entire galaxy. This is essentially what we're doing. We are tracking all of the relativistic jet formation and particle acceleration in our galaxy. The project which produced these data was ThunderCat for the first 5 years. And we now have a follow-up project called XCAT. Okay, so let's talk about some of the astrophysics that we get from these data then. So this is part 3 of the 4 parts of my talk. And this is the longest part, which contains the meat of what we have observed of these large-scale decelerating jets and what we think we can learn from them. So I'll start off by asking some fundamental questions about black holes, astrophysics, and jet production, which I think are relevant well beyond the field of X-ray binaries, and we can see whether or not we can use these data to answer some of these questions. So we still don't know how black hole jets are formed. There are lots of people doing GRMHD simulations, but in most cases, it is simply impossible to cover all dynamical, physical scale and time scales and include all physics, particularly radiation physics. So we still don't really understand how black hole jets are formed. Very importantly, we need to know how much energy they carry. We have an idea of how energy is liberated as it falls down towards a black hole. Indeed, it's very, very simple. You drop something down towards a black hole, you change that gravitational potential into liberated energy. That energy can go in a number of different ways. That energy can be released as radiation. That energy can somehow contribute to the formation of powerful jets, which carry away kinetic energy, or that energy can cross the black hole event horizon, which means it's advected. And by this, I should be clear, I don't just mean that the matter crosses the event horizon, which is the ultimate fate of nearly all of the matter, but that the matter essentially is still hot while it crosses the event horizon. In that case, it's advected across the event horizon. So it's very important for our understanding, essentially, of black hole thermodynamics to understand how much energy these jets carry. Are they powered by black hole spin? This is a long-lasting question, which we've been attempting to test with these stellar mass black holes. In some parts of the AGN community, I think this is the accepted paradigm, but I think I'd like to emphasize again, this really isn't proven in any realm of astrophysics yet. And of course, how do they transport the energy? We know they carry a lot of energy. How do they transport it to the surrounding medium? So we don't really know how they're formed. I've already made that point, but we do have some sense of when they are formed. So this is a schematic diagram which we sketched out 20 years ago. And I'll just put up this. This is all you really need to care about for this upper part of this diagram, that luminosity increases as you go up, and accretion state is essentially the x-axis. What we find in the stellar mass black holes is that there are phases when there is a steady jet, just like the jets you see, for example, in FR1 radio galaxies. There are phases when there is a powerful transient jet, which seems to carry a lot of energy and moves fast. And this may be something like ejections observed from blazars. And there are phases where there is no jet produced at all. This is 2/3 of the picture, you could argue. And then there is a third part of the picture, which is also very important, which is the connection to winds from accretion disks. And this is something that Theo is now one of the world leaders on. So we can essentially have a nearly complete empirical picture of what is going on in these stellar mass black holes. So we understand that what we see here, the X-ray and radio emission, tells us something about the accretion and jet processes. And essentially, the accretion processes dominate the radiation that we see from these black holes. The jets dominate the kinetic feedback, and the winds dominate the matter feedback. And we've managed to map out this nice empirical picture. So I can't tell you exactly how the jets are formed, but I can tell you when they're formed. And some of the data we have are really exquisite. So let me show you a couple of examples of those data. So here's a detailed example. This was for a new stellar mass black hole, which was discovered in 2019. Its name was Maxi J 1820 + 070. And this is what happens in this field. There are X-ray monitors surveying the sky. There is a black hole that hasn't had a high accretion rate for several decades, i.e., since before X-ray astronomy begun. So when it next goes into an outburst, this is a new source for us and we discover it. So what you're seeing here, ignore this iconic picture for a moment. I'll come back to it in a moment. This is time. So these are tens of thousands of seconds. This is an X-ray power spectrum. The y-axis is frequency in hertz, and the grayscale you see is power. And this is the evolving dynamical power spectrum of emission from close to this black hole. The reason I have this figure up here is because the emission that you're seeing producing this variability close to this stellar mass black hole is exactly the same range of scaled gravitational radii as is being directly imaged by EHT. Okay, so these are completely synergistic and complementary ways to approach black holes. This emission is occurring within tens of gravitational radii of the black hole. So what you saw for this source, 1820, is that there were perhaps 10 or 15,000 seconds where there was a lot of power at a range of frequencies. There were some characteristic frequencies which were drifting to higher and higher frequencies. And we think as the emitting region got closer and closer to the black hole. And then there was a phase where all of this broadband power disappeared. And for a timescale of order, perhaps 1,000 seconds, the entire X-ray emitting region close to the black hole just oscillated with a frequency of about 4 hertz. This is quite remarkable. And again, let me emphasize, this is the region of the accretion flow very, very close to the black hole. The radio observations we have at high angular resolution close to this are also remarkable. So there are radio observations, so the black hole is here, this little cross here. There is an extended jet moving away in this direction. And radio observations by Callum Wood at Curtin in Australia showed that this component was moving away from the black hole at about 0.3 C. But Callan then also found that there was a theta component, component C, which was launched around here. So we know this jet, the slow-moving one, was launched around here. We know now that there was another component C, which was launched around here. So later, but it's actually moving at greater than 0.9 C, and presumably either passed through component A or missed it if they were slightly misaligned. So this is the quality of the data we have. We really have exquisite quality data for connecting jet launch to the physics of accretion. Okay, so I'm going to use the MeerKAT observations to try and answer the first one of these astrophysics questions. How much energy do black hole jets carry? So one of the things we can do, if we have a synchrotron emitting component, if we can isolate it in our radio images, if we can measure the size or estimate the size and the luminosity of it, then we can calculate its internal energy. This is the minimum energy approach, which was first worked out in the 1950s by Jeff Burbidge and was applied to AGN to demonstrate that the lobes of AGN had enormous energy contents. However, there is a problem, which is that the internal energy we measure is actually a function of the true internal energy, but also of the Doppler factor, the Doppler emission, sorry, the Doppler shift of the emission, both relativistic beaming and a shift of frequencies strongly modifies what we measure. And here, just to be absolutely clear, large gamma is capital gamma is the bulk Lorentz factor of the flow, so essentially how relativistic it is, and theta is the angle to the line of sight. And then there is an additional complication, which is the total energy. So this is including the kinetic energy now will be something like this bulk gamma times the internal energy. So we need to know how fast these ejecta are moving, but it's very, very hard to tell how fast jets are moving when they're on axis. And again, this is not entirely intuitive if you work in a field of relativistic jets, where your jets are nearly always viewed on axis. This doesn't appear to be a logical statement, but in fact, it happens with off-axis jets. So let me demonstrate. So here, you see the bulk Lorentz factor of a jet, and here you see the apparent speed that you measure on the sky of these jets. And I've plotted this in steps of 10 degrees for angle to the line of sight. And remember that X-ray binary jets are typically observed at about 60 degrees to the line of sight because these objects are selected on their X-ray emission, which is isotropic. So let's first start with a typical X-ray binary then. So 60 degrees to the line of sight. This is this line here. So what you see is that at low Lorentz factors, increasing the Lorentz factor or decreasing it does appear to make a small change in the apparent speed that you measure. However, once you get to above about 4 or 5 Lorentz factor, there's absolutely no change whatsoever. So I cannot tell whether my X-ray binary jet has a Lorentz factor of 1,000,000, 30, or 3 from observing its proper motions. It is impossible to tell. For most other classes of relativistic jets, blazars and GRBs, the situation is more like the blue line, 10 degrees, and then if I measure an apparent speed of 5, in fact, the true Lorentz factor is about 5, and it only starts to deviate from linear at very high Lorentz factors. So what we're seeing in X-ray binaries, these off-axis jets, is a complete contrast to what you see with GRBs or blazars, or in fact, even the class of jetted TDEs. It's an added complication, but it also means we have some advantages that we can use these data for. So how do we try and measure the energy, and how do we try and work out what the true Lorentz factor was? Well, deceleration is the key. So as you know, this is an image of Hercules A, AGN, and this is a schematic of a GRB jet interacting with the surrounding medium. The key is that if we can measure how these jets interact with the surrounding medium, then we can actually get a much better handle on what their total launch kinetic energy was. And we are taking now inspiration from both the AGN and GRB fields. So there are observations of, so we have made observations of decelerating ejecta with MeerKAT. I'll show you some examples in a moment. And if you apply GRB shock models, so this is this formula is a version presented in a recent paper by Francesco Caritanuto, then we can actually measure something here. We can measure a kind of pseudo energy, which actually is a function of the true energy, the surrounding interstellar medium density, and the opening angle of the jet. And this is based, as I say, on GRB models, which are essentially themselves subsets of relativistic spherical blast wave models. And these are essentially the same models that were developed by, for example, Taylor back in the 1940s, where he was able to look at images of the Trinity atomic bomb tests and work out what the energy of the atomic bomb had been just from photos of the expansion speed of the cloud without knowing any of the details. There is a paper, it's been a very nice experience. There's a paper being led by James Matthews in Oxford, where essentially all of us in Oxford have got together for about the last 2 years and tried to understand how we might apply analytical models from other fields to these X-ray binary jets. And we're considering quasi-spherical models. We're considering models which are more blob-like, and we're considering models where the jets are expanding laterally and trying to understand whether we can apply them to our data. And I think the answer is yes. I think that the results we get from applying these models are probably accurate to within a factor of 10 for estimating the energy of these jets. So the very first example of a decelerating jet, and essentially the only good example prior to MeerKAT, was this source XTJ1550, which was discovered as a new black hole in 1998. This is an image on arc-minute scales of the jets. The black hole is here. One side of the jet is here. The other side is here. So this is time in days, up to 2,500 days, and this is a projected separation in arc seconds. We knew that the outburst occurred here. The jets were observed later on by accident. In fact, myself and my colleague Stefan Corbel just took an observation a few years later, and we were like, hang on, that source wasn't there when we looked 2 years earlier. That's how we discovered these jets. We didn't expect to see them. And we saw that these jets are moving at, relatively low speeds, and yet they must have been launched here. So these lines here suggest that perhaps they've been decelerating like this. So this, the interpretation of these data was first applied by Wang et al. And there's a paper by Steiner and McClintock as well. But now we have many, many examples with MeerKAT. So let me show you the first example. The first example was this source J1820, which is the same source for which I showed you the X-ray power spectrum earlier. So here are a sequence of images with MeerKAT made and reported by Joe Bright. This was published in Nature Astronomy in 2020. The black hole is here. The approaching jet, which is slowly displacing itself from the core, is on this side, and the receiving jet is on this side. So there are some beautiful things about these data. As I say, we have an idea that the jet must have been launched. There was a peculiar phase that only lasted of order thousands of seconds. We were also able to make a direct measurement of the radio source size, of the ejector size at about 90 days, and then we observed the ejector to decelerate. So here are the separation. This is the separation, again, arc seconds against time, of the approaching side of the ejector. At first, it looked like it could be linear, and then later we clearly saw it decelerating. We also see just about that the receding ejector are decelerating at all. And it really allows us to put together this beautiful picture. We can tie back these ejections all the way down to a period with an accuracy of better than an hour to the launch time of these ejector. So now, in fact, we have a huge ensemble of these large-scale jets from MeerKAT. So here I show you now, this is time since ejector launch in days, 2,000 days, angular separation in arc seconds, up to 1 arc minute. These are the data from 1550, which I showed you, the source from back in 1998. And these are all the observations which we've made with MeerKAT of large-scale decelerating jets. There's a huge number of papers. These have all been published. This is submitted, and all of these are in preparation. All of these sources are showing these resolved jets. To put it in context, I should say also that for 1550, we saw that these large-scale jets much later on. So we're still occasionally going back to these jets to see if we see late-time deceleration phases. And I should also point out this source 1348, which had a very fast initial separation and then slowed down very, very dramatically here. And just to emphasize something, that prior to our observations with MeerKAT, 90% of resolved observations of X-ray binary jets were in this box. They were observed within 100 days of jet launch and were observed on angular scales of less than 1 or 2 arc seconds. This is a completely new parameter space apart from these observations of 1550. So we can take this model, which Francesco was developing and extrapolated from GRBs, and Francesco can fit this to a number of X-ray binaries. So he's fitted it to this source, 1820, which I've been talking about, and 2 other black holes. The model is fit to the light curves, and very roughly you can think that the initial gamma naught, the Lorentz factor comes through in the initial apparent speed and deceleration curve. and the energy comes from the stopping distance. It's not quite as simple as that, but these are the main things involved in the fit. And what we see then is we see effective energies, which is the most important thing here, of between 10 to the 45 and 10 to the 46 ergs. This is for an ISM density of one particle per cubic centimeter. If we drop the ISM density perhaps down to 10 to the -3 particles per cubic centimeter, which is really towards the lower edge of the ISM densities in our entire galaxy, the so-called coronal phase, and we see we have kinetic energies of perhaps 10 to the 43 to 10 to the 46 ergs. We know from our images that the jets don't have opening angles much larger than 1 degree, so this can't be, this aspect here can't be an error. So we see these are very large numbers. We may also take numerical observations, so a completely different approach now. Instead of doing analytic studies, we may take numerical simulations, apply them to our data, and see what we get out. So these are observations which are being led by Katie Savard, a PhD student, and myself and James Matthews in Oxford, running on the Pluto relativistic hydrodynamical code. And these simulations started off with our directly observed quantities from MAXI J1820, the source I've been talking about a lot. So here you're going to see 3 panels: density, pressure, the pseudo-emissivity, i.e. what an ideal radio telescope would see, tracer, which is the launch material, which was there at the start, and the bulk Lorentz factor. So we propagate these simulations forward over several hundred days, which is the timescale over which we observe these jets. So we see lots of interesting things. We see a high-pressure cavity is formed behind the ejector. We see that you should, in principle, be able to resolve structured emission. We see that the initially launched material, the so-called tracer, is spread out behind the jet, and then we see that there is material that retains relatively, good, highly relativistic velocities or moderately relativistic velocities, and also there's a bow shock that propagates out into the interstellar medium. I'll show that movie once more. So again, this is from our start conditions that we think we estimated fairly well from radio observations propagating over the deceleration lifetime of 1820, which is a couple of hundred days. Katie's also producing a code called blob render, which will actually be able to produce accurate radio images directly from these simulations. And I think this will be very important for future radio observatories. So these are the parameters that Katie put into her simulation, which, as I say, were directly measured or estimated from observations. Again, she needed to stop having ridiculous energies in the jet. She needed the ISM density to be pretty small. Also, if there's anyone in the room that works on AGN jets, she needed the blob to be over dense with respect to the interstellar medium. Otherwise, it couldn't propagate very far. In a lot of models for continuous jets from AGN, in fact, the jets are under dense compared to the surrounding medium. So then, what is the power of black hole jets? We are getting more accurate values, I think, but they're large. So these are recent estimates just from our MeerKAT data. There is lots of other work on this field, but they also end up with large values. So Joe Bright, just from observations, got an estimate of between 10 to the 41 and 10 to the 43 ergs. Katie's numerical simulations are getting 10 to the 44 ergs. Francesco's analytic modeling, GRB models, gets 10 to the 43 to 10 to the 46 ergs. These are large numbers. What about the power then? Well, we think that this jet was probably formed during this odd phase that we saw in the power spectrum, which was of order 1,000 seconds. So if we then just divide by this 1,000 seconds, we get powers in the jet of between 10 to the 38 and 10 to the 43 ergs per second. So this is up to 10,000 times the Eddington power during that period of jet production. And I should say, by comparison with other sources where we see multiple ejections, there is really no way to make this phase much longer. So this top end here, this is causing a real problem, whatever your favorite model for the powering of jets, even spin powering of black hole jets. It finds it very, very difficult, essentially impossible in any of the existing literature to produce 10,000 Eddington going into a jet. And how is the energy transferred to the ISM? Through working with Katie on these simulations, I personally have got a much better understanding of how this may be taking place. So this is a sketch of her simulation. The result, in fact, these are, sorry, it's not a sketch. These are the properly summed values from a simulation over 150 days. We see a simulation which is essentially dominated by kinetic power, And then by about 80 days, this is essentially turned to internal power. We see that the simulation is essentially dominated initially by the kinetic energy of the ejector, and by the end has turned into heating of the interstellar medium. We also can observe what is happening within the ejector themselves. So these are 6 days, 45, 75, and 82 in the simulation. And we see a reverse shock, this line here, contact discontinuity, propagating back into the ejector. And this actually would be resolvable at late times. And what we see is that this reverse shock, which propagates back into the ejector, this is what causes them to remain bright for a long time. If they were just adiabatically expanding, they would fade within a few days. But in fact, this shock propagates back in the frame of the ejector. They're not moving, the IS-7 has hit them, and this keeps the ejector relatively hot and bright. And then finally, Katie always sees that the X-ray binaries produce these large cavities around them. These cavities will continue to expand because they're overpressured into the IS-7 for maybe 20 years, but then it takes about 1,000 years for them to be refilled by the IS-7. We just divide their size by the sound speed of a typical IS-7. The recurrence time for these sources is typically much less than 1,000 years, at least, of course, the ones we know. And so this is actually an explanation for why these jets are propagating into low density cavities, because the X-ray binaries create the cavities themselves. So I'll just show you some other highlights of the program. This was a black hole, Maxi J1848, which was discovered. This is probably a black hole in a globular cluster. This is a sequence of images taken every week for 2 years from this source. This source had almost no attention paid to it because it wasn't a very interesting X-ray source, and then it soon became sun obscured, so it couldn't be observed very well. We saw very bright jets propagating away from this central black hole, which intriguingly appear to brighten and fade multiple times as they propagate away from the black hole. And it's fascinating that we're seeing these in a globular cluster environment where we may have some good idea of the interstellar medium density. The initial results from this are published in Bahraini et al. This is the one neutron star I'm going to show in this talk. This is a source which is similar to SS43, except we know it's a neutron star. The neutron star is here. This shape here is the natal supernova remnant. I have no idea what this is. It's something to do with it. But the interesting point is that on small scales, we know there is a jet going in this direction. For the first time, our MeerKAT observations show this circular structure, and you can see, I hope, you can see this faint blowout here. So essentially, the jet from the neutron star has punched a hole in the surrounding supernova remnant and is inflating it surrounding it. And this is an almost unique opportunity to get to estimates of power of jets from a neutron star. And then finally, let me move to this source. This is from Zhang et al., which we've just submitted. 4U1543, this was an old source, but we reobserved it in outburst a couple of years ago. We saw high proper motions away from the source. The bottom line is that because the angle to the line of sight for these jets is small, we were able to measure a very high minimum Lorentz factor. Depending on the distance to the source, the minimum Lorentz factor is between 5 and 8. And let me just reiterate this point. With these X-ray binaries, we're seeing the jets largely off-axis. But for the fastest AGN for blazars, we see them close to on-axis. It is entirely possible that black hole X-ray binary jets are as relativistic as the bulk of AGN, and that this point has been misunderstood for 30 years. When the first paper came out of the first superluminal motion X-ray binary source 30 years ago, it was stated in that paper the Lorentz factor was around 2. This was always understood by some of us to be only a lower limit, and now we see that the lower limits are much higher, and we have a better understanding of selection effects, and I think it's entirely possible that the stellar mass black holes produce jets just as relativistic as those from AGN. All right, so I'm just going to, I think I have 3 slides left, and I just want to tell you about something else that has come out of these data, because we now have an ensemble population which is large enough to do statistics on and test against things like black hole spin and jet precession. So here is the distribution of measured beta gamma. You can think of this as essentially gamma, Lorentz factor, for X-ray binary jets for all cases where the jets have actually been directly observed in radio images and we've tracked their motion. So it's a histogram. The largest bin has 6 in it. The highest Lorentz factor we've measured is 5. You can just about, I hope, see these gray bars on to the right of these two columns, which indicates for all of these sources, these are just lower limits on the Lorentz factor for the reasons I've been explaining. So what do we find from this ensemble? Well, we find that black holes show a range of speeds from slow. Some black hole jets are slower than 0.3 C, and some have Lorentz factors greater than 5. And there are at least 2 different sources which show jets with very different speeds. So black holes can produce slow and fast jets. We see that black hole jets are faster than those from neutron stars. This is perhaps not unexpected, but we can confirm it statistically from our sample. Perhaps most intriguingly, we find that the most relativistic black hole jets repeatedly propagate along a fixed axis. So now if you look at the colors in this histogram, you can see that all of the points I've marked as blue, these are black holes where we've seen more than one ejection, where we've measured a high Lorentz factor, and we find that the direction it moves in the sky is exactly the same as what we saw at previous times. So they're tied to a fixed axis, the most likely fixed axis in this system. These systems has to be the black hole spin. In contrast, the precessing jets, which are the red bars here, are at best only mildly relativistic. And just for those of you who have never seen this, this is a beautiful movie you can find on the internet that was never published of precessing jets from SS433. So the point here is that only jets which are locked to the spin of the black hole are highly relativistic. We have a sample where we see multiple examples of precessing jets. They are never highly relativistic. So we might perhaps sketch out a model, something like this, which is essentially the middle panel here says there are 2 ways that jets can precess. One could be that the accretion disk is precessing around an axis, which would correspond to the binary axis, or it could be there is an inner torus, which is precessing around an axis, which is the black hole spin axis. We think we see both cases in these sources. But when the accretion disk, or when the accretion rate goes to very high levels, the accretion flow becomes aligned with the black hole spin. This is a well-known general relativistic effect called the Bardeen-Peterson effect, and I think that's what's producing this locking. So perhaps this is the first ever connection, directly observed connection between jets from black holes and the black hole spin, because we see they have different states, but when they're really fast, they're locked along a fixed axis. So some of you will know that the most commonly cited model for extraction of black hole spin to produce jets is by Blandford-Znajek, and that predicts that the jet power should increase with spin. Because this power is mainly kinetic, you might expect that the jet speed increased with spin. So we tested for a correlation of the jet speeds with reported spin measurements. There is none. There is no correlation at all. There are 3 different methods of trying to estimate the spin of stellar mass black holes and X-ray binaries. For each of these 3 methods, there's a pretty big sample which overlaps fairly well with our sample of speeds. There is no correlation. This is consistent with previous failures, which ourselves and others have done to find any correlation of any jet properties with the spin. So perhaps the jets align with the spin through the Bardeen-Peterson effect, but somehow the spin doesn't affect the speed or power. This is still powered by the accretion flow, but it's not actually extracting the spin. Or perhaps some of the spin measurements are wrong, and I'll leave you to wonder about that. All right, my last slide. Before I do my summary, I would like to thank the whole Institute very much for hosting me for these last 3 weeks and the next week when I will be here. I'd like to thank Teo and Montse in particular for being extremely welcoming and supportive hosts. I have a very strong collaboration going on with people here in X-ray binaries, and I think that we will be developing a new collaboration going forward on the connections between X-ray binaries and AGN. I'm here for another week. My scientific summary is that jets from black hole X-ray binaries are really vital. And remember this, they're the only population of systems where we see off-axis jets regularly. And that's really important. MeerKAT's an incredible radio telescope. I hope you agree. The observations of the large-scale decelerating jets have really revolutionized the field, and I think probably most importantly in giving us a range of ways of measuring the jet power and finding that it's very, very high. These are really too high, even if they're almost going into near vacuum. I don't know how to explain that. And then our ensemble study shows that the very fastest jets seem to be tied to the black hole spin axis. But when we try to make a direct connection of any properties to reported spin measurements, we don't find any. Thank you very much for listening.
Thank you, Rob, for a really interesting talk. Now it's time for questions. We have at least a few minutes before moving to the coffee break. So does anybody in the room have a question for Rob?
Thanks for the beautiful talk. Really enjoy it. I work on AGN, so I was all the time like trying to put the two things together. So one thing is that I didn't completely get the point of, you said that in some sources you observe the jets, like the two sides of the jets are redshifted. How is that possible?
The hand-waving explanation that the GRB fields give, for example, but of course it just comes from the Doppler factor, is that unless you observe a jet within an angle of 1 over gamma radians, then you see it redshifted. So essentially what happens, if you take a jet, for example, of Lorentz factor 3, essentially this means that the time dilation effect takes over from the geometrical effects. Right? So here's a view, for example, and this is called V3. Sometimes the jets are exactly in the plane of the sky. There's a moment, and on both sides are redshifted, and that redshift is a pure time dilation from the relative motion. Yeah.
Thank you. More questions?
So, Rob, I think I actually never understood very well the why this MeerKAT revolution happened. So, because in the past we have telescopes, arrays such as the VLA, and why is this MeerKAT doing this so many new things?
It's a very good question, and it's essentially chance. So we put in part of the X-ray binary monitoring part of our MeerKAT program was essentially to monitor black hole X-ray binaries, compare them to simultaneous X-ray observations we make with Swift, and do this radio X-ray plane, which is still actually a kind of what's turned out now to be a secondary science goal. But the point is that if you observe these things for weeks, then essentially at some point you start to see these jets. And the VLA, and this is a general point about these highly oversubscribed facilities that don't have long-term program, it will typically give you a few epochs, and it'll typically give you these epochs early on, and then that's it. So the VLA could easily have detected these jets. In several cases, we found jets, we got VLA observations, and sure, the VLA is detecting the jets and has some beautiful results. But it's because, you know, in 1820, the first one we saw, it was a surprise. The angular resolution of MeerKAT is 2 or 3 arc seconds, right? All previous jets, as I tried to indicate earlier, were essentially seen on angular scales less than 1 arc second. There's no way, we knew there was no way we were ever going to resolve jets. And then one day, you know, 6 months later, we were like, the source looks resolved. And then we found the jet. So it's the long-term monitoring that basically turned it up by accident.
Hi, thanks for this very nice talk. I'm also working with AGN, and at some point in your presentation, you mentioned the jet powers that can be up to 10 to the 43 ergs per second. This is in X-ray binaries. So this is as powerful as a compact radio jet in AGN. So how can this be possible? No.
Yeah, so we've been trying to estimate the power of jets from X-ray binaries for a long time, and have lots of different methods. And sometimes you get relatively low values, sometimes you get these high values. We now have, you know, these beautiful data. The deceleration really gives us this new insight. We have different methods, and we're just getting these very high values. So, you know, for the interstellar medium into which the jet propagates is a key determinant of how far the jet makes it. We have to select a density of 10 to the minus 3 particles per cubic centimeter to explain what they do. If you look at the distributions of ISM densities in our galaxy, that is the density you get in the lowest density component in our galaxy, the so-called coronal component. And even then, we're getting these very high powers, very high energies. How do we do it? I don't know. Some of the energy estimates, as I said, are 10,000 times Eddington. The most recent works on extracting spin energy of black hole jets, the so-called MAD, magnetically arrested disks models, would say that you can increase the jet power by perhaps a factor of order unity from Eddington. Perhaps, let's be generous, let's say 10. 10,000 Eddington, I don't know. The only way to do it from our modeling is to have them essentially propagating into extremely low densities, perhaps 10 to the minus 6 particles per cubic centimeter. And I've no idea if that's plausible. We're already at the lowest possible densities. So it's a real puzzle. Yeah. I mean, of course, you know, the original idea of extracting spin energy from a black hole is a Penrose process. And in principle, you could have a rapidly rotating black hole and stop it. And then you'd release an enormous amount of energy, right? But so there's nothing in basic physics that says you can't extract more, but all of the current models for extracting it from accretion flows actually can't explain these very high values.
Thank you. So I'm not at all from the fields, but I have a question about the distance that you can achieve with the explosion of matter. I was wondering, like, what is the distances depending of the ISM quantity that you can reach? Like, how far can you go away from the sources?
Didn't put it on my slide. I didn't put it on my slide in the end, but there's interesting geometrical effects in here as well. But essentially, we see the jets in 4U 1543. Don't worry, it's the really fast one. We see the jets in that propagate to about 5 light years before they start decelerating. And that's the furthest that we've seen. The interesting geometrical effect is that we see it propagating to 5 light years. That's deprojected in 1 year, which is like, that sounds a bit odd. And it's just because we see this, you know, it's the apparent superluminal motion, it's the light travel time. So we're seeing the jets propagating out to parsec scales, essentially. In terms of the ISM, which is relevant to your question, it's very hard to make any direct in situ measurements of the ISM, though. So we don't know, unless we are lucky enough at some point to see the jets run into like a molecular cloud or something. That would help. Yeah.
Okay, I think we have a last question from the Zoom, from Anshon Alberti. He says, hi, Rob, how does SKA meet will improve the results of MeerKAT in this field of stellar black holes? What extra info will you be able to obtain?
What extra input from what, sorry? From SK Mid, yeah, okay. So nearly all the observations I showed you so far were with L band. This is the 1.4 gigahertz band, which has the 21 centimeter line. We are now making observations at S band. So we've doubled the angular resolution in the last year. And MeerKAT should have received, SK Mid, sorry, which MeerKAT will morph into on a timescale of maybe 5 years, will increase the angular resolution again through frequency by a factor of 2 to 3, and then by another factor of maybe 3 from slightly longer baselines. So the angular resolution will increase dramatically. One of the predictions from Katie's models is that by about 100 days, maybe earlier, we will start directly resolving the ejector. So you'll remember from these movies, we see instabilities occurring at the front and the side of the jets. As it's transferring this kinetic energy into the interstellar medium, we should be able to spatially resolve those with SK Mid. But I think that's the most exciting thing. And of course, it will be so sensitive that we'll be able to make these observations, a 5-minute observation will give you the separation and of the ejector, their luminosity, and at late times will spatially resolve them as well. So this is a low-cost program for SK Mid.
That's great. Okay, so as I don't see any more questions in the room, you have more of them. We will be moving to the coffee, scientific coffee now. So let's thank the speaker again. It seems there were a very last minute question. You want to reply to him? Just quickly. Okay. Yeah. So it's the very last one. Okay, so it says, thanks for the very nice talk. The simulations assume normal electron, proton, or pair plasma electron positron content of these jets. And how does this affect the energy estimate? Have you checked the particle content with the circular of near polarization observations?
Yeah, this is a good question. I hope you can hear me. Those simulations I showed, they're assuming 1 proton for 1 electron, cold protons, and we require most of the mass to be in the protons. We are also going to explore other compositions later. Thanks.
Okay, thank you.